Welcome to the deep dive.
Hey there.
So today we're jumping straight into a really core idea in geometry, locus.
Mhm.
Now, I know that might sound a bit, I don't know, academic, maybe a little dusty from school.
Yeah, it can sound quite formal, can it? Locus.
Right. But stick with us because it's actually a surprisingly powerful way to think about shapes and, their relationships.
It really is.
The word itself, it's Latin, isn't it? For place.
That's right, yeah. Think location or locality, same root.
So essentially what we're talking about is
Yeah.
uh, the path a point traces out when it has to follow a specific set of rules.
That's a perfect way to describe it, yeah. Imagine like a satellite orbiting the Earth at a constant altitude.
Oh.
That path it takes, the orbit, that's its locus.
Ah, got it. A real-world example.
Exactly. And our goal, really, for this deep dive is to kind of nail down this fundamental concept.
Right.
We'll look at the definitions, work through some key geometric problems, unpack some important theorems, all based on the material we've got here.
Yeah, try and give you that sort of aha moment.
Precisely. That moment where you see how locus really provides a foundation, for understanding why geometric things are the way they are.
And what's cool is once you kind of get it, you start seeing geometry less as just static pictures
Mhm.
and more as these like dynamic relationships playing out.
Right.
Okay, so let's get our hands dirty. First scenario.
Let's do it.
I've got two parallel lines. Let's say they're sitting nice and neat, 4 centimeters apart.
Okay. Classic setup.
Now, what if we have a point that's moving, but the rule is it must stay the exact same distance from both of those lines? What kind of path does it trace?
This is a great place to start. It really illustrates the core idea. The sources guide us through this pretty clearly.
Yeah.
They suggest, picturing it or even marking points that are perfectly in between. So if the lines are 4 centimeters apart.
The point has to be 2 centimeters from one line and 2 centimeters from the other.
Exactly. Now, if you imagine plotting out a few of those points, what shape starts to emerge?
Well, it wouldn't wiggle around, would it, if it's locked into being exactly in the middle?
Right.
It feels like it just has to trace a straight line itself.
Precisely. And that's our first key takeaway. The locus of a point that stays equidistant from 2 parallel lines. It's always another straight line.
And not just any line.
No, exactly. It's
Yeah.
parallel to the original 2 lines, and it sits smack bang in the middle.
Okay. Simple, but powerful. It shows how that condition, that rule, dictates the resulting shape.
Mm-hmm. Okay, let's switch gears slightly.
Right.
Forget the 2 lines for a second. Now, picture just a single fixed point. Let's call it O.
Just O. Okay.
And our moving point, P, has a new rule. It must always stay the same distance away from O. Always. What path does P trace now?
So not equidistant from 2 things, but a constant distance from one thing.
Exactly. This is another really fundamental one. Again, the material suggests visualizing it. Mark several points, A, B, C, D, whatever.
All at that fixed distance. Let's call it R from O.
Yep. What shape are you getting when you connect those points?
Well, you can almost see it, can't you? If every single point is exactly R away from O, it's got to sweep out a perfect circle.
Bingo. It's a circle. The fixed point O is the center, obviously.
And that constant distance R is the radius?
Exactly. So the locus of a point maintaining a constant distance from a fixed point is simply a circle.
Makes perfect sense. Okay, moving on. Let's get a bit more formal now with Theorem 3.
Right.
This one tackles the locus of a point that's the same distance from not parallel lines, but 2 intersecting lines. What's the story here?
Theorem 3 tells us something pretty neat. The locus of a point equidistant from 2 intersecting lines is actually the pair of lines that bisect the angles formed by those intersecting lines.
The angle bisectors, okay.
And the source material actually lays out a formal proof, which is helpful to see why that's true.
All right, let's try and unpack that proof. So I've got 2 lines, say AB and CD, crossing at point O.
Yep.
And we pick a point P somewhere in one of the angles formed, let's say angle AOC.
Okay, inside the angle.
And the condition is that P is equidistant from line AB and line CD. So the perpendicular distance is the same.
Correct.
How do we prove rigorously that P must be on the line that cuts angle AOC exactly in half?
It involves a little construction, which is common in geometry proofs. From point P, you drop perpendiculars down to the lines AB and CD.
Okay, straight down at 90 degrees.
Yep. Let's say these perpendiculars hit the lines at points L and M. So PL is perpendicular to AB, PM is perpendicular to CD.
Right.
This creates 2 right-angled triangles, POL and POM.
Ah, triangles. I see where this might be going.
Exactly. Now, what do we know about these triangles? We know PL equals PM, right? That was our condition. P is equidistant.
Yep.
We know angles PLO and PMO are both 90 degrees because we constructed them as perpendiculars.
Right angles.
And crucially, both triangles share the side PO. That's the hypotenuse for both.
Okay, so right angle, hypotenuse is the same, and one corresponding side, PL and PM, is the same. That's familiar. RHS.
You got it. Right angle, hypotenuse side. The RHS congruence rule.
Which means the two triangles are identical copies of each other.
Precisely. Congruent. And if the triangles are congruent, then all their corresponding parts must be equal.
Including the angles.
Including the angles. So angle POL must be equal to angle POM.
And if PO splits the angle AOC into two equal smaller angles.
Then PO is the angle bisector of angle AOC by definition. So P has to lie on it.
Nice.
Okay.
That proves one direction. But what about the other way around, the converse?
Good point. We need to show that any point on the angle bisector is definitely equidistant from the lines.
Right. How does that work?
So now we start with a point, let's call it Q, that we know is on the angle bisector of AOC.
Yep.
Again, we drop perpendiculars from Q to the lines AB and CD, meeting them at, say, R and S.
So QR is perpendicular to AB, QS is perpendicular to CD, creating triangles OQR and OQS.
Exactly. Now, what do we know here? They share side OQ.
Yep.
Because Q is on the angle bisector, we know angle ROQ equals angle SOQ.
Right. That's the definition of the bisector.
And angles ORQ and OSQ are both 90 degrees by construction.
Okay, so we have an angle, another angle, and a shared side. Is that AAS angle side?
It is. Or you could think of it as ASA if you consider the 90-degree angles, the equal angles at O, and the shared side OQ, either way.
The triangles OQR and OQS are congruent.
They are, and therefore, the corresponding sides QR and QS must be equal in length.
Meaning Q is equidistant from lines AB and CD. Perfect.
And as the theorem notes, this logic works for points in all four angles formed by the intersection.
Ah, so the full locus isn't just one bisector line.
No, it's the pair of lines that bisect all the angles. They form a cross shape themselves, a very useful result.
Definitely is. Okay, theorem number 4. Let's keep the momentum going.
All right.
This one shifts focus again. It's the locus of a point that stays the same distance, not from lines, but from two fixed points. What does theorem 4 tell us?
Theorem 4 states that the locus of a point equidistant from two given fixed points is the perpendicular bisector of the line segment connecting those 2 points.
Okay, let's visualize. 2 points, A and B, just sitting there.
Fixed points.
And we have a moving point, P, such that the distance PA is always equal to the distance PB.
PB, that's the condition.
The theorem says the path P traces is the perpendicular bisector of the line segment AB. Let's break that down. Why?
Okay, so first, draw the line segment connecting A and B.
Done.
Finds exact middle point. Call it O. So AO equals BO.
Good point. Got it.
Now connect our moving point P to this midpoint O.
Okay, drawing PO.
This gives us two triangles, AOP and BOP. What do we know? Well, PA equals PB. That's the given condition.
Right.
AO equals BO because O is the midpoint.
Yep.
And the side PO is common to both triangles. It's shared.
Wait a second. Side, SSS.
Exactly. The side congruence rule strikes again.
Meaning triangle AOP is congruent to triangle BOP. They're identical.
They are, and therefore their corresponding angles are equal. So angle AOP must equal angle BOP.
Okay, and those two angles, AOP and BOP, they sit next to each other on the straight line AB.
Right, they form a linear pair. Their sum must be 180 degrees.
So if they're equal and they add up to 180,
they each have to be 90 degrees.
A right angle. So PO is perpendicular to AB.
It is. And since O is the midpoint, PO is the perpendicular bisector of AB.
So any point P that's equidistant from A and B has to lie on that line.
That's the first part proven.
And naturally the converse. We need to show that any point on the perpendicular bisector is definitely equidistant from A and B.
Right. So pick any point Q that you know is on the perpendicular bisector PO.
Okay, Q is on the line.
Look at triangles AOQ and BOQ. We know AO equals BO. O is the midpoint.
Yep.
We know angle AOQ equals angle BOQ because they're both 90 degrees. It's the perpendicular bisector.
Right angles again.
And side QO is common to both.
Okay, so this time it's OSI, angle, side, SA.
I guess AS congruence, exactly.
Which means triangle AOQ is congruent to triangle BOQ.
Correct. And therefore, the third sides, the hypotenuses in this case, must be equal. AQ must equal BQ.
So any point Q on the perpendicular bisector is indeed equidistant from A and B. The theorem holds both ways.
Fantastic.
Absolutely. And this one is super important for constructions, like finding the center of a circle that passes through 3 points, or just drawing perpendiculars.
Yeah, you can really see the practical applications starting to stack up. Speaking of which, the source gives us some examples. Let's look at example 3, part I. A bit more complex setup here.
Okay.
We have a triangle ABC. A line BX bisects angle ABC, so it cuts that angle in half.
Got it. Angle bisector.
Then another line CY is drawn perpendicular to side AB, and Y is specifically the midpoint of AB.
Okay, perpendicular and Y is the midpoint.
These two lines, CY and BX, they cross each other at a point P.
Right.
The goal is to prove that this intersection point P is equidistant from points A and B.
No.
P, A, if U, P. How do we tackle that?
This solution here uses congruent triangles again, focusing on point Y, the midpoint. If you draw a line segment connecting A to P...
Okay, draw AP.
Now look at the two triangles formed using the midpoint Y, triangle APY and triangle BPY.
APY and BPY.
Okay, what do we know? AY equals BY because Y is the midpoint of AB.
Give it.
The side PY is shared between both triangles.
Common side, right.
And angle AYP and angle BYP are both 90 degrees because CY was constructed perpendicular to A.
Ah, so we have side angle, side again, SAS.
Exactly. SAS congruence tells us triangle APY is identical to triangle BPY.
And if they're identical.
Corresponding parts are equal, so side AP must equal side BP.
Meaning P is equidistant from A and B. Done. Neat.
It works out nicely.
Okay, then part 2 of the same example looks at a different point. It looks at point D, which is where the angle bisector BX from before hits the other side of the triangle, side AC.
Right, the intersection of the angle bisector and the opposite side.
And we need to prove that this point D is equidistant, not from points, but from the sides AB and BC.
Okay, equidistant from two lines. That should ring a bell. Theorem 3 territory.
The angle bisector theorem.
Essentially, yes. But let's prove it using the method shown. The idea is to draw perpendiculars from point D down to the sides AB and BC.
Okay, perpendicular from D to AB, call the meeting point N. Perpendicular from D to BC, call the meeting point M.
Good. Now consider the two right-angled triangles formed, DBM and DBM.
DBN and DBM, okay.
They share the hypotenuse BD.
Right.
We know angle DBN equals angle DBM because BD is on the line BX, which bisects angle ABC.
Equal angles at B, yep.
And angles DNB and DMB are both 90 degrees by arc construction.
So we have angle, angle, and a shared side, the hypotenuse BD. AAS congruence.
Correct again. AAS means triangle DBN is congruent to triangle DBM.
And therefore, the corresponding sides opposite the equal angles must be equal. So DN must equal DM.
Exactly. And DN is the distance from D to AB, and DM is the distance from D to BC.
So D is equidistant from the two sides. Proven.
It flows directly from the properties of the angle bisector.
It really ties back nicely. The source then quickly mentions a couple more. Example 4, finding a point on the base of a scaling triangle equidistant from the other two sides.
Yeah, that's just a direct application of Theorem 3, right?
Yeah.
Draw the angle bisector of the vertex angle where it hits the base is your point.
Exactly. And example 5 sounds like a construction challenge. Find a point P that's both equidistant from points B and C and equidistant from lines AB and BC.
Ah, combine two conditions.
Yeah, so you use two loci at once.
Precisely. To be equidistant from points B and C, P must lie on.
The perpendicular bisector of segment BC, Theorem 4.
Right, and to be equidistant from lines AB and BC, P must lie on.
The angle bisector of angle ABC, Theorem 3.
So where do you find the point P that satisfies both conditions?
It has to be where those two lines, the perpendicular bisector and the angle bisector, intersect.
Exactly. The intersection point is the only point that lies on both loci simultaneously.
It's like a geometric treasure map. Using these loci as the X marks the spot lines.
That's a great analogy. Now, section 16.5 in the source pulls together a really useful summary list of key loci.
Oh, good. A recap.
Yeah, it lists 8 common scenarios. We've covered a few in depth already.
Let's run through them quickly. Equidistant from two fixed points.
Perpendicular bisector.
Equidistant from two intersecting lines.
The pair of angle bisectors.
Fixed distance from a fixed point.
Circle.
Equidistant from two parallel lines.
Parallel line midway between them. Okay, number 5 is interesting. A given distance from a given line.
Right, we touched on this. It's not one line.
No, it's 2 parallel lines, one on each side of the given line at that specified distance.
Makes sense. Above or below, or left or right, depending on orientation. Okay, number 6 involves circles, midpoints of equal chords in a circle.
Their locus is another circle, concentric with the first one, because equal chords are always the same distance from the center.
Ah, Okay. And number 7, midpoints of parallel chords in a circle.
Their locus is a diameter that's perpendicular to those parallel chords.
Right, you can picture those midpoints lining up. And the last one, number 8, equidistant from 2 concentric circles.
Unsurprisingly, it's another concentric circle right in the middle, halfway between the original two.
It's really quite elegant how these rules generate these familiar geometric forms. The summary also stressed a couple of important points about describing a locus properly.
You need to state both the type of figure, line, circle, pair of lines, etc., and its exact position and orientation.
And that crucial two-way street idea. Every point satisfying the condition must be on the locus.
And every point on the locus must satisfy the condition. It has to work both ways for it to be the true locus.
Yeah, no exceptions allowed.
Exactly. And the material even points towards some further exercises to explore these ideas, like exercise 7.
What was that one?
It asks for the locus of a point P, given 2 fixed points A and B, such that angle APB is always 90 degrees.
Angle APB equals 90 degrees.
That sounds like the angle in a semicircle theorem.
Precisely. The locus is a circle with the line segment AB as its diameter. Any point P on that circle, except A and B themselves, will form a 90-degree angle APB.
Cool application. What about exercise 8? That one puts the point P inside a circle, and it needs to be equidistant from 2 points A and B, which are on the circumference.
Equidistant from 2 points A and B. That's our theorem 4 again. Let's be the perpendicular bisector of the chord AB.
Exactly. And within the circle, that perpendicular bisector is a diameter, or part of one.
And exercise 9.
Briefly mentions finding a point P at a specific distance from 2 intersecting lines. How would you approach that?
A specific distance from a line that was a locus type 5, wasn't it? The pair of parallel lines.
Yep.
So for 2 intersecting lines, you'd construct the parallel lines for the first given line, one on each side at the required distance, and then do the same for the second intersecting line.
Right.
And the points P would be where these constructed parallel lines intersect each other. You could get, up to 4 possible points?
Exactly. It shows how you combine these basic locus ideas to solve slightly more complex problems.
So wrapping this up, it feels like this whole concept of locus, it's not just, a definition to memorize.
Not at all.
It's a really fundamental principle. A powerful way to think about and describe the paths points take when they follow rules.
Absolutely. The theorems, the examples we walk through, they provide a solid toolkit, really, for tackling all sorts of geometric constructions and proofs. Understanding locus gives you a more dynamic view of geometry.
Yeah, you stop seeing shapes as just static things on a page and start seeing them as like the result of movement, constrained by these very precise conditions.
It reveals the underlying order and, frankly, the elegance in geometry. How simple rules lead to these predictable, often beautiful forms.
It really does. It makes you wonder, where else does this idea pop up, this idea of a path or a set defined by specific conditions?
That's a great question to ponder.
Like, could you apply it in physics? The trajectory of something under gravity and air resistance, is that a kind of locus?
You could certainly argue that. The path is dictated by the laws of physics acting as the conditions.
Or even in, data science. The set of all data points that meet certain criteria, maybe that's an abstract kind of locus.
That's a fascinating parallel. A set of points in multidimensional space, defined by rules or constraints.
Yeah. It prompts you to think about any situation, really, where something moves or changes or simply exists according to a specific set of rules. That underlying idea, that's locus in action.
Well said.
This has been really insightful. Definitely gives you some food for thought.
Yeah.
And I suspect, for anyone listening, you realize this is probably just scratching the surface of where a loci can take you.
There's always more to explore.